Before I work the next problem, I'd like to draw a graph of a plane, a three-dimensional object based on a linear equation. And so here's our equation: 2x plus 3y plus 6z equals to 12. So the reason this is a three-dimensional object is because there are three variables. And with the three variables varying, one could represent length, another width, and the other one height. So it's not terribly productive always to attempt to graph in 3 dimensions on a 2-dimensional board or on paper. And so we're rather limited on what we can do with graphs in 3 dimensions. But I wanted to show you how we could try to represent this. And then this will lead into something else I have to say about solving these systems of equations. Alright, so the way we typically do it in math is to draw our axes this way. Now I've only drawn the positive axes. This one is the x-axis, and imagine the x-axis is actually coming out of the wall straight toward you. I can't obviously draw out here, but we can give the illusion that it comes out from the wall. I don't think it's a very good illusion, but it's about the best we can do. This is the y-axis, and then the vertical is the z-axis. Now these choices of x, y, and z are pretty typical of what we do in calculus or anywhere else where we might attempt to draw a three-dimensional graph. And I've only drawn the positive half of those axes. So this is the positive x-axis, positive y-axis, positive z-axis. So the z-axis literally extends below. Y goes to the side and z goes into the board. I'm sorry, x goes into the board. Alright, so look at this equation, and it's a linear equation where each of these has a power of 1. And so I'm going to use an intercept method of graphing. If y and z are both 0, then x would be 6. So here's 6 out here. And then if x and z were both 0, and you solve for y, then y would be 4. So I'll say that's about there. And then if x and y were both 0, solve for z, you'll get 2. So, oh, I made a mistake, didn't I? Y would not be, yes, it would be 4. Never mind. Okay, but z would be 2. Alright, so 6, 4, 2. And all I've drawn are the three points which intercept the axes. But it forms a plane in 3 dimensions. The objects, the linear objects in 3 dimensions forms a plane, but all I'm representing is just the part of the plane that exists in the first octant. And so try to imagine this slanted triangle here appearing in the first octant. And there it is. Now it literally extends forever in all directions, so it's like having this board infinitely large in all directions. That would be a true plane. So all we can do is represent a little bit there. Alright, so that's a plane, and a point on the plane would have x, y, z coordinates. So this point, who knows what that is? Maybe it's a 2, and I'll call it a 1, and then, oh, maybe a 1. I don't know. It's a little hard to interpret that in 3 dimensions, so that's obviously why we don't do a whole lot with these. Okay, well, we'll refer back to this in a little bit. Let's solve another problem.